Hey, and welcome back to Carter Physics. Last time we said that if you raise something up, you give it potential energy, right? So this ball we said is about 1.8 kilograms. So if I lift it up from the ground about 2 meters in the air, it's got like 35.3 joules worth of potential energy. Today we want to worry about what's going to happen if I let that go. Now, we all know it's going to fall. And as it falls, it's going to go faster and faster and faster on the way to the ground. So as it moves toward the ground, it's losing potential energy. It went from 2 meters to 1 meter. Eventually it's going to be down at 0 meters. So what I want to know is, as that potential energy goes down, because the height is decreasing, where did it go? Well, what happens to the speed of the ball as it goes down? Right? It starts off sitting still, so it's going 0, and it goes faster and faster and faster and faster. So if I raise that ball up and let it fall, we can see that all that potential energy that it started with at the top slowly converts or quickly converts to kinetic energy, so that by the time it hits the ground, it's all speed. It's turned into kinetic energy. But those 35.3 joules of potential it had at the top are now 35.3 joules of kinetic energy at the bottom. So the energy was conserved. That's what we mean when we talk about the conservation of energy. So when we're talking about conservation of energy, what we mean is the total energy stays the same. It's conserved. You don't gain or lose any along the way. It just transfers. So for the ball dropping, we could say that the total energy, I'm just going to call it TE, at the top equals the TE, the total energy, at the bottom. Okay. At the top, you could have potential energy from gravity plus kinetic energy, plus if there was spring potential, but there's not. So that's your top, and that would be equal to your potential plus kinetic everywhere along the way, but we'll say at the bottom. At the top of the thing, all it had was potential, so the kinetic energy was 0. So, right, that's 0. It didn't have any kinetic. At the bottom, all it had was kinetic. The height was 0, so the potential had gone to 0. So all that potential energy it had at the top was turned into kinetic energy at the bottom. So you had mass times gravity times the height at the top equals 1/2 times mass times the velocity at the bottom squared. We can use that to determine how fast the ball was going when it got to the bottom. Okay. So when we want to go ahead and do this, I know you can't see me, but that's not what's important. We want to figure out how fast the ball was going at the bottom. The mass of the ball, we said, was 1.8 kilograms. Gravity on Earth is 9.8 meters per second squared, and the height of that thing was about 2 meters up, right? And that's equal to 1/2 times the mass, 1.8 kilograms, times the velocity squared. So the velocity squared, that's our unknown. That's the thing we don't know we've got to solve for. When I multiply 1.8 times 9.8 times 2, I get about 35.3. So at the top, it had 35.3 joules of potential energy. Right? That's how much energy it started with. That's how much it should have the entire time. 1/2 times 0.8 would be 0.9 kilograms times v squared. Right. Now what do we got to do? Right. Since it's velocity, we hope the units are meters per second. Let's see what happened. We had joules over kilograms. We knew from before that a joule, right, was a kilogram meter squared over second squared. We got that with kinetic energy a long time ago. So if we have joules on top and kilograms on bottoms, we divide that by kilograms. Right. Joules over kilograms, right? Kilograms goes away and you get meters squared over second squared. So these are really meters squared over second squared. When you take the square root of that, you're going to get just meters per second. So the speed at the bottom of that ball, by using conservation of energy, that the potential at the top turned into kinetic at the bottom, we know that when it hit the ground, the ball was going 6.3 meters per second. Pretty cool. Okay, so we figured out how fast the ball was going when it got to the ground from being dropped 2 meters. But as it was falling, it was going faster and faster. So my next question is, how fast was it going when it got to the 1 meter mark? When it was still 1 meter up, but it was falling, it had some speed. So some of the potential had been turned into kinetic and some was kinetic. We should be able to figure out how fast it was going at that point. So it should look something like this. Okay, for the problem of the ball halfway down, we could say the total energy at the top, the total mechanical energy, so the potential plus the kinetic at the top equals the potential plus the kinetic everywhere along the way, right? The total stays the same. That's the idea of conservation. So you have potential plus kinetic at the top, and that would be the potential plus the kinetic everywhere along the way, right? Not just at one place. This total stays the same. So mass times gravity times height at the top would give you the potential at the top. 1/2 mass times velocity squared would give you the kinetic energy at the top, which in this case, right, it was sitting still. So that's 0. That would be equal to the potential energy at some point plus the kinetic energy, 1/2 mv squared at some point. So if I add the potential and kinetic at any point together, they should add up to that total. We said earlier that the total was 35.3 joules. So this is 35.3 joules. All right, I got that by taking the mass, 1.8 kilograms, multiplying it by gravity, 9.8 meters per second squared, and a height of 2 meters. So my mass was 1.8 kilograms, gravity, 9.8 meters per second squared, and my height was 2 meters. So now putting those numbers in over here, I want to know what this velocity is when you're only 1 meter up. So this is going to be 1 meter. .64 joules is how much potential it still has. So if I subtract that off from the total, 35.3 minus 17.64, I get like 17.64. So 17.6. Which should make sense, right? That half of the energy, 17.6 joules, is potential and 17.6 joules is kinetic because it's halfway down. So now 17.6 joules is how much kinetic energy it has, right? I subtracted from the total. The energy that was left is the kinetic. So I can divide by the 1/2 times 0.8. 0.9 kilograms v squared. So we'll divide. And then remember, we take the square root of it. And we get like 4.4. So anywhere along the way we can find the velocity. We just happen to figure out at 1 meter up, it's 4.4 meters per second. Right? You're going to get a few examples to do next. The top of this sign is 1.5 meters above the ground. So if I take my 1.8 kilogram ball and I hold it right there, 1.5 meters above the ground, when I let it fall, how fast will this ball be going when it hits the ground? Ready? One of the coolest things we can do with conservation of energy is figure out how fast things are going on ramps. It's not as straightforward as just dropping stuff because you don't just have straight gravity on a ramp. But energy is still energy. So if we have a cart, one of our little Go Direct carts from class, and you can see the top front corner of it is 15 centimeters above the tabletop, right? And the ramp goes down so that it's level with the tabletop at the bottom. So my first question is, how much potential energy does this cart have at the top of the ramp? To find the potential energy of the cart, we need to know the mass of the cart, what gravity is on Earth, and the height of the cart. We know the height is 15 centimeters, which is 0.15 meters, and we know the mass of the cart is 0.28 kilograms. So we can find the potential energy. Some quick math tells us that the cart has a potential energy of 0.4116 joules at the top of the ramp. When I release the cart and let it go down the ramp, all of that potential energy was converted into kinetic energy, just like if it fell. It took a little longer going down the ramp, but it still turned all that potential to kinetic. For the ramp, the total energy was equal to that potential energy at the top, 0.4116 joules. So the cart sitting at the top of the ramp had all of that potential, and as it went down to the bottom, all of that potential was converted into kinetic. So we could use that to find the velocity at the bottom of the ramp just like we did with the ball dropping if the cart would have fallen off the back of the ramp. At the bottom, the potential energy would be 0 because the height would be 0, so all the energy is kinetic. That means the kinetic energy at the bottom is 0.4116 joules. Plugging that into the equation, we can solve for the velocity and get at the bottom of the ramp, the cart was going 1.7 meters per second. An example for you to solve. How fast is that cart going when it's about halfway down the ramp, when it's 0.08 meters up, if it started from 0.15 meters up? Remember that some of the energy is potential and some is kinetic at that point, but the total of all the energy should still add up to 0.4116 joules for the cart, because the total energy it had at the top was 0.4116 joules, and the conservation of energy says that amount should stay the same. So, your question, how fast is the cart going as drawn on the ramp?